Now, in the last video of this course, we looked at the concept of wait groups in Go and how we could use them to effectively block the execution of our application until all of our Go routines had finished their own execution. In this video, we're going to be looking at the concept of a mutex, or a mutual exclusion, and how we could use it to effectively guard the critical sections of our code. So what do I mean by guard our code? Well, when we start to introduce concurrency into our Go applications, we need to start worrying about things called race conditions and ensuring that we're not updating specific variables or values in an incorrect order. Okay, so just to give you an example, let's think about a time when we have an application that deals with a bank balance. Imagine we had a customer with a balance of £1,000 and the customer tries to deposit £500 to his account. Now, one Go routine would see this transaction. It would attempt to read the initial value, which would be £1,000, and then it would do all of the processing involved in terms of adding £500 to the existing balance. However, imagine at the same moment, a charge of £700 is applied to his account to, say, pay for his mortgage. Well, this second transaction would be picked up by another Go routine, and without the appropriate guards in place, it would attempt to read the initial value and then update the value based on this original value. Now, if you were expecting this to work normally, you would expect the balance to be first increased by £500, and then £700 would then be subtracted from that, which would leave you with a value of £800. However, as the second transaction has read the initial balance of 1,000 and then proceeded to update based on that original balance, the customer might be left out of pocket and he might be left with only £300 in his account. Now, this isn't an ideal situation, and it's something that we can effectively guard against using mutexes. Cool, so let's dive into the code and see how we could create an application that uses mutexes. So let's start off by creating an account struct that'll have a balance of type int. And let's say account is equal to account. Let's set the original balance as 1,000. And then let's create a couple of methods off of this account struct. Now let's start with the withdraw method. So withdraw, let's take in a value, which will be of type int. And just for simplicity, let's add a wait group, which will be a pointer to a sync.wait group. And then let's do the following. So let's do a.balance minus equals value wait group dot done. Cool. So just fix that typo. And then let's do the following. So let's do a Go routine, or let's create a new wait group first. So var wait group is equal to sync.wait group. Let's do Go account.withdraw. Let's pass in, say, £700, and let's pass in the wait group. So as we're adding something to the wait group, we need to do wait group.add, and we'll do 1 for now, and then let's do wait group.wait, and then let's just do a print line saying account balances updated. Cool. So let's validate that everything's working as expected. And let's also print out the balance. So fmt println account.balance. So go run main.go in the terminal to run this application. And as you can see, £700 has been withdrawn from the account balance of 1,000. Cool. So let's define the deposit method. So let's do deposit. This will take in a value and the wait group sync.wait group. And let's do a.balance plus equals value and wait group dot done, like so. Once again, let's go into the main function and let's do go account dot deposit, and let's do 500 passing in the wait group, and let's update the counter to 2 here. And then let's run this in the terminal. So go run main.go. As you can see, account balance is now 800. Cool. So in this case, we were given the correct balance for our account. However, in a more complex example, there is the possibility that this turns into a race condition that bites us more often than we'd like to in production. Now, this is how we're going to guard against the potential race condition here. So we effectively need to evaluate the critical sections of our code. And these are going to be lines 13 and 18, in which we update the account balance. Now that we've identified these critical sections of code, we now need to wrap these sections of code in a mutex. So let's do that now. So I'm going to create a new mutex and sync.mutex. And let's just in the main function, let's create a new mutex. So var m sync.mutex. And let's say mutex is equal to &m, like so. Cool. So we've got this mutex on the account. What we can now do is within these methods, we can do a.mutex.lock. And then once our critical sections of code have finished executing, we can do a.mutex.unlock. Now we've done this for the withdraw method. Let's also do this for the deposit method. Perfect. So by adding these two sections of code, or these two lines of code within each of our methods, we're effectively turning what could potentially be a race condition into synchronous blocks of code. So we have one mutex defined off of our count struct. Now, whatever coroutine gets there first is going to try and acquire the lock. So it's going to say, I want to perform my critical section of code. This is the mutex I need to unlock or lock. Attempt to lock this. If we can't lock it, we're going to block the execution of our method until we can acquire this lock. And then once we have locked this mutex, we then have the safety to update any critical sections of code or execute any critical sections of code. Now, once we have processed this critical section of code, we then say, I'm finished, and we unlock this mutex. Now, once it's unlocked, as I said, the other coroutine that is trying to acquire the lock will then be able to acquire that lock and then perform its critical sections of code before then unlocking. So let's go into the terminal and do go run main.go. And as you can see, there's no real tangible difference between the outputs of our potentially race condition laden code and the safe code that we have defined here with our mutexes. Cool. So we now have an application that uses a mutex. There are a couple of things that we have to consider when we're defining code that uses mutexes. Now, the big thing is we have to try and avoid a thing called deadlock. Now, deadlock occurs when we have a coroutine that has locked our mutex and will no longer allow the execution for any other coroutines. And we can see an example of that if we comment out the unlock methods here. So let's try and run our application. So go run main.go. We should see our application panics, and we should see that fatal error, all coroutines are asleep. We have entered a state of deadlock. So when writing concurrent applications that use mutexes, bear in mind that every path, whether it be the happy path or the sad path within your code, has to call this unlock method at the end. Now, the final thing to consider when writing concurrent applications that use mutexes is that in this instance, we've effectively turned our concurrent application into a synchronous application. So only one of these functions can really execute at one time, and they'll be executing one after the other. So that is definitely something you'll want to consider if you're writing highly performant applications, as you will definitely see an impact in performance when you start using mutexes. However, in the same hand, you're still guarding yourself against race conditions, which could potentially lead to poor outcomes for your customers or your clients. Cool, so that's all we're going to cover in this video. Now, just to recap, in this video we've covered the concept of race conditions and how it can impact our concurrent applications. We've then looked at how we can instantiate a mutex and use it to guard ourselves against these race conditions by calling the lock and the unlock methods on these mutexes around our critical sections of code.